Hello, welcome to this tutorial on microstructure model of AM Pravah. In this, we are going to learn about the process parameters and simulation settings in microstructure model. Microstructure model in AM Pravah is used for predicting the grain evolution in LPBF process. The model uses probabilistic method called Monte Carlo simulation to simulate the grain formation. Since in this model, we are not solving fluid equations or energy equation, the thermal profile calculation is done using the Rosenthal equation. The module does consider the material properties while calculating the thermal profile. Let's move to the GUI. So inside microstructure module, we have this settings tab. Clicking on this will open the window for inputs. So let's first see the material properties. For all our properties, we have solidus temperature, thermal diffusivity, and thermal conductivity. Solidus temperature basically means our melting temperature. There, for laser properties, we have laser scanning speed, laser power, D for sigma or laser spot diameter. For chamber conditions, we have initial temperature or preheat temperature. Then we have layer thickness for multi-layer simulation. Then we have our initial substrate height, or we can call it substrate thickness. Then we have alloy heat absorption fraction. Basically, is a substitute for Fresnel coefficient we have in macroscale module. So it basically decides how much of the total energy will be absorbed in the material. So practically this value ranges from zero point 0.3 to zero point 0.7 for the LPB process. So usually for powder bed the values will be much higher, about zero point 0.7 or maybe higher than that. And for molten surfaces, molten interfaces, the point will be lower, like about zero point 0.3. We have made here an approximation. So we are giving a zero point 0.5 value throughout the process. For our scanning pattern, we will provide CSV file with XYZ coordinate and the time coordinates. Then in simulation preferences, we have a number of spin states. So practically, we don't know how many different grains will be there in our microstructure. So to differentiate any two grains, we will require different grain IDs for the different grains. Since we don't know how much grains will be there, we the minimum number of different grain IDs that we require are will be equal to the how many neighboring grains will be there around us or around some grain in the microstructure. So we have considered 125 swing states, which will be enough for basic simulations. If our grains are much smaller, where a number of neighbors around the grains are so many, maybe 100 or more than that, in that case, maybe we may need to increase this number of swing state. Then we have width adjustment parameter and depth adjustment parameter. So basically these are the correction factors to correct our width and depth. So our main aim here is not to calculate the melt pool, but here we are calculating only the grain evolution. Since this module does not solve the safety equations, we will correct our width and depth from the data we get from our experiment or from our macro scale simulation or our melt pool simulation. Once we have our corrected width and depth adjustment parameter by iterative process, we can predict grain evolution in the melt pool. Then we have accuracy. Accuracy is something like a mesh size we have in a melt pool simulation. It can be defined as a small volume inside which we can approximate zero thermal gradient. Similarly, we have performance, which again decides the size of our smallest element that we call as lattice size. Then we have data sharing frequency. It basically decides how much data we want to be saved for the visualization purpose. Then for parallel simulation, we have number of CPU cores. So in this case, 4 cores will be used for the simulation, and total we have 6 cores. So here I have simulated a microstructure. You can see we have used 125 grain IDs. So each color basically represents a grain ID. So let's assume if we have used less number of grain IDs or a less number of spins, then we will have two neighboring grains which will have same grain ID, and we will not be able to differentiate between two grains. That's why we will require enough number of grain IDs to differentiate between two neighboring grains. Here we can see small cubes. These cubes we call it a lattice site. So increasing accuracy will decrease the size of this lattice site, and the number of lattice sites will increase. That will basically make your grains more resolved for visualization purpose. And increasing the grain IDs will help to differentiate between two grains. When I click on save button, the terminal will show the size of our lattice site, which is 3.33 micron. Let's increase this accuracy to 25. Click on save. Now our lattice size has been decreased, which is now 2 micron. Remember how the grains are resolved in this simulation with 15 accuracy. Now we will simulate the same simulation with increased accuracy, which will be 25. I'm saving it, and will click on save all, and I will run the solver. I can click on launch console to see the progress of my simulation. So till now 2% of my simulation has been finished, and here it's showing the approximate estimated time that will be required for the simulation, which is about zero point 0.3 hour. That's about 20 minutes. So we will wait for the simulation to finish. So our microstructure simulation has been finished. Now we will visualize our simulation results. So let's click on show results. It will prepare files for the visualization, and we will be able to see our results. So I will click the reload files. Then I will cut a clip to visualize the top surface of our microstructure. Now in this simulation you can see our lattice size is much smaller than the earlier. So we will have much resolved grains in these results. Let's play this. The black portion basically shows the melted part. As the cooling happens, the grain evolution will start gradually. So this is our final microstructure. So here at some region, you may say there are two different grains which are not they are resolved, but their grain IDs are not much different. So they both showing similar color. So in such cases, we may increase our grain ID so that we can differentiate grains visually better and also mathematically better way for our post processing. Let's see from the explain. So this is how this is our melt pool, and this is how the grain evolution has been happened. I can cut this in Y plane so that we can see the side view. Yeah, so this is the side view. So let's now simulate the multi-layer, and also we'll see how we can create a scan pattern for the microstructure simulation. I will go to my project location. So in documents, inside tutorial, here I have created my project. Inside dataset, this is our default pattern.csv, which is a default. So here in first column we have our layer number, then we have time, then we have xyz coordinate, and then we have laser off and on condition. So for the laser off condition, basically this is our cooling time. So we basically take our laser out of our domain, uh, and that is counted as the cooling time in the microstructure simulation, and we'll provide the particular time for that. In microstructure module, the scanning speed, laser scanning speed, will be taken from here. So it doesn't matter what value you put here. You can put any values here. So basically this xyz are important, and this laser on off conditions are important, but don't keep it blank here, and you will be giving your laser scanning speed from here in bit of a second. Let's see the multi-layer scan pattern. Here we have a two-layer scan pattern. So we have layer number one and then layer number two. So from layer number one to layer number two, we have our laser off, and we are moving to the next point immediately with a small time interval. So here you can see that here you can see the time increment is not much. So we provide a very small time for the movement of the laser, and then we move to the next layer. So let's now simulate the multi-layer. I will choose this two-layer scan pattern. Then I will click on Save button. I will reduce my accuracy so that the simulation will be faster. Save again, go back, and save all. I will click on the Run Solver. Let's wait for the simulation results. So now our simulation has been finished. Now we will visualize our results. So I will click on the Show Result. I will reload files, find new files. Now I will cut a clip, or maybe I can cut clip in by. Yes, let's play the simulation. So this is our first layer, and this is our second layer. So you can see these are two melt pools we got, and you can see these two melt pools have not fused properly. So maybe we will have to decrease our layer thickness, or maybe we have to calibrate our melt pool shapes. So let's reduce our layer thickness to maybe 30 micron. Save it and save all, and I will again run this simulation. So our simulation has been finished. Now we will visualize our results. I will click on the show results. Mm, Let's reload the files. Now I will cut the clip in Y plane. Let's see if our layers have been fused together to form a uniform build. So this is our first layer, and yes, this is our second layer. We can see how our grains from two layers has been merged to form a single grain. You can also visualize this from X direction. Yeah. So this is our two layer build. Yes. So this is it. If you have any questions, write in the comment box. If you want to watch more tutorial videos on AM Pravah, visit our YouTube channel and don't forget to subscribe. Thanks for watching.